Now I'm going to talk about the sensitivity report in Excel. I'm going to explain graphically how allowable increase and decrease can be derived. So we look at this problem where a company tries to determine its weekly production quantity of two products. X1 and X2 are the production quantities. Its goal is to maximize its weekly profit. 8 and 5 are the profit margins of the products. It is subject to several constraints. For example, the first constraint says that the total consumption of plastic material cannot exceed its availability of 1,000 pounds. Now let's look at the first part, the upper part of the report. This part of the report tells you what happens if the coefficients here, 8 and 5, are changed. First, let's look at the feasible region of this problem. The feasible region of this problem is this area. And this is the isopropyl line that goes through the optimal solution, which is the red point. Now, let's start to change the coefficient over here. Let's say this one, the first coefficient, 8. Let's try to reduce that. Let's reduce it to, say, 4 and see what happens. Turns out that if you reduce it to 4, you draw the line, it looks like this. And this is the isopropyl line. It turns out that the best objective function still goes through the red point, which means that this is still the optimal solution. And the other observation we find is that when we reduce this number, the line becomes flatter. Okay, so we can keep reducing this line, and it turns, as you can imagine, it will keep going through the red point, but it just gets flatter. And as you can imagine, at some point it will become like this, coincide with this constraint, and it turns out that this is when we reduce the coefficient to 3.75. So at this point, if we further reduce this coefficient, what will happen is that, well, first of all, the line becomes flatter, but because it becomes flatter, this red point is not optimal solution anymore. It turns out that the optimal solution will become this point. So from this little exercise, we find that this coefficient, the first coefficient, can be allowed to reduce from 8 to at most 3.75 without changing the current optimal solution. That is why we have an allowable decrease of 4.25, which is a difference between 8 and 3.75. So that's what happens if we try to reduce that coefficient. Now let's try to increase it instead. Increase it from 8, and let's do the same exercise. Well, previously when we reduce that number, the line becomes flatter. So you can imagine if we increase this number, it would do the opposite, making the line steeper. And as you increase this coefficient, the line becomes steeper, and you can imagine that at some point, which turns out to be when it becomes 10, this line, isopropyl line, will coincide with this constraint, and that is the highest number you can increase without changing the optimal solution. And that is why we have an allowable increase of 2, because 10 minus 8 is 2. If you increase this coefficient beyond 10, then the optimal solution will not be this point anymore. So together with the previous slide, we know that, well, here the first coefficient can take any number between 3.75 and 10 without changing the current optimal solution. That is why we have a range of optimality of this. And now if you look at the sensitivity report, the allowable increase is 2, allowable decrease is 4.25. These are exactly the number we showed in the previous two slides. Now let's see what happens if you change the right-hand side value of a constraint. I'm going to first define two terms. The first term is called slack. Slack is the difference between right-hand side and left-hand side value in a less or equal to constraint. Economically speaking, slack refers to the amount of unused resource. Think about the first constraint in this problem, which says the total consumption, which is on the left-hand side, cannot exceed the availability, 1,000, which is on the right-hand side. So if we have positive slack, it simply means that the current production plan does not use up all of the available resource. Second term I'm going to introduce is surplus. It is simply, again, the difference between left-hand side and right-hand side value, but this is for a greater or equal to constraint. Apply our context. If we have a greater or equal to constraint, it means that we need to consume at least certain amount of resource. The certain amount of resource is the right-hand side value. So surplus here essentially means the amount by which our consumption exceeds the minimum requirement. The minimum requirement is the right-hand side value of the constraint. So a constraint would have either slack or surplus, depending on its sign. Sometimes a constraint is so-called binding. It is called binding if its left-hand side value is the same as its right-hand side value. So in this case, its slack or surplus is simply 0. Now let's look at the example of this problem we're solving. So this is a feasible region. There are 3 lines that determining the feasible region. These are representing the production time constraint, plastic constraint, and production mix constraint. Turns out that the optimal solution is this point. And you can see that this is the intersection between this constraint and this constraint. Or in other words, with this optimal solution, this equality holds, and also here the equality holds. We call this constraint binding because at the optimal solution, this becomes equal to. This is also binding because in the optimal solution, this sign becomes equal to. But this constraint is non-binding because with the optimal solution, this sign will be strictly less than. So for these 2 binding constraints, we have 0 slack. For this non-binding constraint, it turns out that we will have positive slack because the less sign holds at the optimal solution. We're actually interested in seeing what's the impact of the change of right-hand side value on the objective function. Well, now with the introduction of binding and non-binding constraints, we can better answer that question. So now let's see what happens if a constraint, the right-hand side value of a constraint is increased by 1. So again, looking at the feasible region, this brown line is the ISO curve, ISO profit line for the optimal solution. Okay, here's the optimal solution. If you plug in the coordinates of this point, optimal solution, into objective function, you'll find out the profit is this number, 4360. Now let's suppose that we increase the right-hand side value of that constraint by 1. In other words, this number goes up from 1000 to 1001. Let's see graphically what happens. This is what happens. Turns out that this line will move up to here, which essentially means that the feasible region is enlarged with this new dark blue region. So now, what is our optimal solution? Well, it turns out that the ISO profit line can move up and improve the profit. The new ISO profit line becomes the dotted brown line. And this is the new optimal solution. At that point, the new maximum profit if you plug the coordinates of this point into the objective function, turns out to be this number. Apparently, this is larger than what we used to have. We call the difference of these two the shallow price. So the shallow price is basically the increase in profit as a result of change of the right-hand side value. Specifically, shallow price is the increase in the objective value when the right-hand side value goes up by 1. Let me show you a little bit detail on how I derive the shallow price. So from the previous figure, we know that when the right-hand side of the new constraint becomes 1001, the optimal solution is determined by the intersection of these two lines. So the optimal solution is simply the intersection, which can be obtained from solving these two equations with two unknowns, and you will get this number. We plug it into the objective function. This is the resulting optimal profit. So the shallow price of this constraint is simply the new profit minus the original profit, so that's 3.4, the shallow price. But now what happens if we actually increase the right-hand side value of that first constraint by 2? Well, you'll find that graphically you can confirm that the optimal solution is still at the intersection of these two constraints. So we can solve again for the intersection by solving this system of equations, getting their coordinates, plugging it into objective function, we get the new profit here. So the profit will actually increase by, actually if you carry out the algebra, is 2 times the shallow price over here. So what do we get here? What we find here is that the change in the optimal profit is simply shallow price times the amount of increase in the right-hand side value. What happens to the non-binding constraint? Previous slides talk about increasing the right-hand side value for a binding constraint. Now let's look at the non-binding constraint. Let's say the second constraint over here. We have 2 non-binding constraints. Turns out that for the non-binding constraints, the shallow price is 0. Let's graphically see why. So here is the graphical representation. This is the non-binding constraint of our interest. This is the optimal solution as we showed previously. Let's say if we increase this number from 350 to 351. Graphically, it turns out that this red line will move to the right to here, which means that the feasible region actually gets larger a little bit. However, the optimal solution is still determined by the other 2 constraints. The optimal solution is irrelevant to this non-binding constraint. So, despite the increase in the right-hand side value here, there's no change to the optimal value. Therefore, shallow price is 0. So, just to sum up, what do we observe? 2 important observations. First, if we change the right-hand side of a binding constraint, it may very likely to change the optimal solution. That is because the objective value is constrained by the right-hand side of a binding constraint. Secondly, if we change the right-hand side value of a non-binding constraint, as long as that change is within the allowable increase or decrease, it will not change the optimal solution. Another important observation is that the shallow price may not be the same. It won't be the same if the change of the right-hand side value exceeds the allowable increase or decrease. So let me show you graphically what happens in that case. Again, the same graph, the same problem, but now let's say the right hand side value of this constraint goes up from 1000 to 1500. That is an increase of 500 exceeding the allowable increase. Graphically, this is the original optimal solution. It is determined by the intersection of blue and green lines, and the brown line is the isoprofit line for the that goes through the optimal solution. Now this number goes up, so the green line actually moves right to somewhere like here. So the new intersection of blue and green lines is this point. What about the new feasible region? Turns out that there's a new area of feasible region. And with that, our new optimal solution actually becomes this point, which is not the intersection of new green line and the blue line. So in other words, what we find here is that when the change of right hand side exceeds the allowable increase or decrease, the new optimal solution will be determined by new sets of constraints, and that makes the shallow price different. So let me just summarize. So let's say we change the right hand side of a constraint and assume we only change that of one constraint. Okay, assuming there's no other changes to the input parameters except for one constraint. Turns out that the allowable increase or decrease, they define the range of values for the right hand side value of a constraint where the shallow price remains unchanged, and we call this range the range of feasibility. In that range of feasibility, the change in the objective value can be calculated very easily. It's simply the shallow price times the amount of change in the right hand side value.